Hello Honors Chemistry students, this is Mr. Spurk, and this is your Chapter 13, Section 2 notes on the nature of liquids. So substances that can flow are referred to as fluids. Both liquids and gases can flow, so we consider air to be a fluid. And this allows them to conform to the shape of their container. So if you remember from physical science, or even very quickly in the beginning of the year, we talked about solids, liquids, and gases. Gases and liquids have no definite shape. They take on whatever shape the container that they are in. So gases and liquids do have a key difference between them. If you remember the kinetic theory, according to the kinetic theory, there are no attractions between gas particles. So the difference is that the particles in a liquid are attracted to each other. And these intermolecular attractions keep the particles in a liquid close together, which is why liquids have a definite volume. So again, we briefly just talked about those intermolecular forces of attraction. That is what holds the molecules of a liquid together. So the interplay between the disruptive motions of particles in a liquid and the attractions among the particles determine the physical properties of liquids. Liquids are much more dense than gases, and so as we increase the pressure on a liquid, it has little effect on the volume. So for example, if I have a pot of water and I go ahead and just push my hand down onto that liquid, the volume of the liquid is not really going to change. If we put a hydraulic press over it, it might decrease a very small amount because we'll be able to squeeze those particles a little bit closer together, but it's not going to have any significant effect on the volume. And the same is also true for solids. If you go ahead and press down on your phone or your computer, you are not going to change the volume of that solid. So we need to start talking about evaporation and vaporization. So vaporization is the conversion of a liquid to a gas or a vapor. So when this conversion occurs at the surface of a liquid that is not boiling, the process is called evaporation. So think about like a puddle sitting outside in the sun. So on the left-hand side, you see we have a diagram for evaporation. If we let a certain liquid sit out, for example, if we let ethanol sit out in a beaker, it's going to slowly evaporate. And the reason it's going to evaporate is because it has enough kinetic energy to break the atmospheric pressure pushing down on it. So we always have atmospheric pressure pushing down. And in order for something to evaporate or to boil, it has to break that barrier and overcome the atmospheric pressure. So when we boil a substance, it makes it much easier because we're supplying the heat. And so when we're supplying the heat, some particles that are maybe even further down in the liquid, like we see here, they start to gain enough kinetic energy. They turn into a vapor. They break the barrier, and they overcome the atmospheric pressure. So again, think about evaporation. We aren't supplying the heat source, so it's a slower process. So evaporation can take place in a closed system or an open system, and the process is much different. So an open system, such as a lake or a glass of water, compared to a closed system, which would be some sort of sealed container. So maybe think of like a can of pop or a bottle of soda. So in an open system, the molecules that evaporate, they can escape the system, right? So if I open up a bottle of pop, those gas particles that form, they can evaporate and break that barrier because nothing's holding them in. However, in a closed system, the molecules collect as a vapor above the liquid and some condense back into a liquid. So if the cap is on it, think about if you've ever left a water bottle or a bottle of pop in the sun or maybe in your car on a hot day. They're going to get warm enough that they break the barrier and become a vapor. But they're going to then bounce all over the walls of the container because they can't escape. And when that happens, we see droplets form. And when those droplets form, that means it's condensed back into a liquid, and they're going to slowly make their way back into the liquid phase. And that process happens at an equal rate. So equal numbers of particles are turning into a vapor, equal numbers are turning back into a liquid. So during evaporation, only those molecules with enough kinetic energy can escape the surface of the liquid. So maybe think about like the game like Red Rover, trying to let somebody break through that barrier. They're only going to break through that barrier if they have enough kinetic energy. So a liquid evaporates faster when it's heated. And again, that's because you're increasing its kinetic energy. More particles can overcome the attractive forces that are keeping them in the liquid state. So again, if we think about water molecules, we have the partial negative end. And here we're showing a hydrogen bond. So we have the hydrogen of one water molecule attracted to the oxygen of another. And this is what keeps them in the liquid state. But if we heat them up enough, the kinetic energy of this water molecule is going to increase, and it's going to break that bond. And then this guy is going to be able to become a vapor. So as evaporation occurs, the particles with higher kinetic energy escape first. The particles left behind then have a lower kinetic energy, which means that as the evaporation takes place, the liquid's temperature then decreases. So we can think about this way. If you're thinking about a race or a marathon, there's always somebody who's out in the front. They have the highest kinetic energy. So if we take the average kinetic energy of everybody in that race, it's going to be a high number. But if I then take away the runner in first place, so their speed doesn't matter anymore, the average is going to go down because we got rid of the highest number. And so then the average kinetic energy of the runners in the race is now lower. So that is why the water molecules in a pot of boiling water they have a lower temperature. So evaporation is actually a cooling process because those vapor particles have higher kinetic energy. And this explains sweating. Why sweating, when we get really hot, you need to sweat so you can cool off. So the sweat that forms on your skin absorbs the body heat, and when it gets hot enough, it breaks the barrier and evaporates, which leaves you cooler. So we also need to talk about vapor pressure. Evaporation in a closed system differs from an open system. So again, think about that container we just saw a few slides ago. So here's our closed container. Some particles do evaporate, but they cannot escape the container. And these particles collide with the walls of the container, producing a pressure. So let's say I just have one water molecule that becomes a vapor. And all it's going to do is bounce around those walls until we open the container, or until it becomes a liquid again. So the pressure of that water molecule bouncing off the walls is what we call vapor pressure. And vapor pressure is just a measure of force exerted by the gas above a liquid. So vapor pressure can change with temperature, and an increase in temperature increases the vapor pressure. So again, think if we have that water molecule in my closed vessel, and now it's in the vapor phase, if we're adding more heat, it's going to move around a lot faster. So the vapor pressure is going to go up. So as temperature increases, vapor pressure increases, because the particles are gaining kinetic energy. And the more particles will break that barrier and become vapor. There's a really great Chemistry for Your Life podcast. It's about 20 minutes. That's all about vapor pressure, and it's called Why Do We Put Lids on Pots to Boil Water? So we can measure vapor pressure with a tool called a manometer, and I just want to talk about real quickly how that works. So at standard temperature and pressure, if we just have air it is exerting a small force on this mercury, which allows it to rise to this level. And this is what we call our zero line. So then if we put ethanol, so now I'm looking at vessel 2, we put ethanol in the beaker, or the round bottom flask, and we cool it, and we keep it at 0 degrees Celsius. There are going to be little particles of ethanol that are going to apply a force to that mercury. And it's going to push that mercury around the U and up the other side. So it's no longer level anymore, as you can see. There's a bit of a difference. And that difference, we just read the markings that are on the glass tube here. And this exerts a pressure, or a vapor pressure, of 12.2 millimeters of mercury. Now if we look over here at vessel 3, we've heated it up a little bit more, which means these vapor particles have greater kinetic energy. So they're moving quicker, they're going to apply more force, they're bouncing off the walls more, they're going to push down more on that mercury, and you can see that the difference here is much larger than the difference here. So when we heat it, the vapor pressure increases to about 43.9 millimeters of mercury. So we need to talk about boiling point. So when a liquid is heated to a temperature at which particles throughout the liquid have enough kinetic energy to vaporize, the liquid begins to boil. And bubbles of vapor are going to form throughout the liquid. They're going to rise, and then they're going to escape. They're going to break that liquid barrier. So the boiling point is the temperature at which the vapor pressure of the liquid is just equal to the external pressure on the liquid. So let's look at a diagram of what that looks like. So at sea level, the atmospheric pressure at the surface of water and 70 degrees Celsius is greater than the vapor pressure. So what that means is we have this atmospheric pressure pushing down at 101.3 kPa. And we have a little bit of vapor on top of this liquid that is much weaker. It does not have a strong vapor pressure. So the atmospheric pressure is much greater, so it's winning, which is why the water molecules cannot become a gas. Then, as we heat the water in vessel 2, we can see that we still have the same atmospheric pressure pushing down, but the vapor pressure has gone up. So here they are equal to the atmospheric pressure. So the vapor pressure is equal to the atmospheric pressure. And that is when the bubbles begin to form. Then in vessel 3, if we go up to Mount Everest, which has about, I believe, 9,000 meters high, the air pressure, or the atmospheric pressure, is much less, which we talked about in section 1. So this force is much smaller, which means that the vapor pressure has to overcome a smaller number. In vessel 2, it had to overcome a number of 101.3. But here it only has to overcome a value of 34. So that's easier to do. So water on top of Mount Everest is actually going to boil at 70 degrees Celsius because it needs less vapor pressure to break the atmospheric pressure barrier. So this is why if you look on different boxes for baking, like I know cakes have this, it'll say if cooking at higher altitudes, cook for this long. And that is all to do with atmospheric pressure. So boiling point is also a cooling process. The vapor produced is at the same temperature as the boiling liquid. And the stored energy of the vapor is much higher. Remember, we talked about that gases have some stored energy. So that stored energy of the vapor is greater than the energy of the liquid. So because of this, a burn from steam is more severe than a burn from the same amount of boiling water, even though they're both at the same temperature. So for example, if you were to dump a pot of boiling water on you, or dump a bunch of steam on you, the steam is going to burn you more because it has higher stored energy. The normal boiling point is the last thing we need to talk about, and it is just the boiling point of a liquid at standard pressure. So at normal pressure, we have a normal boiling point. Because like we just saw from this example here, the boiling points can change